An extended periodic table theorizes about elements beyond element 118. Currently 7 periods in the periodic table of chemical elements are known and proven, culminating with atomic number 118. If further elements with higher atomic numbers than this are discovered, they will be placed in additional periods, laid out to illustrate periodically recurring trends in the properties of the elements concerned. Any additional periods are expected to contain a larger number of elements than the 7th period, as they are calculated to have an additional so-called G block containing at least 18 elements with partially filled G orbitals in each period. An 8-period table containing this block was suggested by Glenn T. Seaborg in 1969. IUPAC defines an element to exist if its lifetime is longer than 10⁻14 seconds, which is the time it takes for the nucleus to form an electronic cloud. No elements in this region have been synthesized or discovered in nature. The first element of the G block may have atomic number 121, and thus would have the systematic name unbilunium. Elements in this region are likely to be highly unstable with respect to radioactive decay, and have extremely short half-lives. Although element 126 is hypothesized to be within an island of stability that is resistant to fission but not to alpha decay, it is not clear how many elements beyond the expected island of stability are physically possible, whether period 8 is complete, or if there is a period 9. According to the orbital approximation in quantum mechanical descriptions of atomic structure, the G block would correspond to elements with partially filled G orbitals. But spin-orbit coupling effects reduce the validity of the orbital approximation substantially for elements of high atomic number, while Seaborg's version of the extended period had the heavier elements following the pattern set by lighter elements. As it did not take into account relativistic effects, models that take relativistic effects into account do not. Pekka Pyukko and B. Fricker used computer modeling to calculate the positions of elements up to Z equals 184, and found that several were displaced from the Madelung rule. Richard Feynman noted that a simplistic interpretation of the relativistic Dirac equation runs into problems with electron orbitals at Z greater than 1, alpha 137, as described in the sections below, suggesting that neutral atoms cannot exist beyond triception, and that a periodic table of elements based on electron orbitals therefore breaks down at this point. On the other hand, a more rigorous analysis calculates the limit to be Z 173. History. It is unknown how far the periodic table might extend beyond the known 118 elements. Glenn T. Seaborg suggested that the highest possible element may be under Z equals 130, while Walter Greiner predicted that there may not be a highest possible element. All of these hypothetical undiscovered elements are named by the International Union of Pure and Applied Chemistry Systematic Element Name Standard, which creates a generic name for use until the element has been discovered, confirmed, and an official name approved. These names are typically not used in the literature, and are referred to by their atomic numbers. Hence, element 164 would usually not be called unhexquadium, but rather element 164 with symbol 164 or E164. As of April 2011, update, synthesis has been attempted for only unlunanium, unbinylium, unbibium, unbiquadium, unbihexium, and unbiceptium. At element 118, the orbitals 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 7s and 7p are assumed to be filled, with the remaining orbitals unfilled. A simple extrapolation from the Alf-Bohr principle would predict the 8th row to fill orbitals in the order 8s, 5 grams, 6f, 7d. 8p, but after element 120, the proximity of the electron shells makes placement in a simple table problematic. Although a simple extrapolation of the periodic table, following Seaborg's original concept, would put the elements after 120 as follows. 121 to 138 form the G-block superactinoids. 139 to 152 form the F-block superactinoids. 153 to 162 would be transition metals. 163 to 166 p-block metals. 167 equals halogen. 168 equals noble gas. 169 equals alkali metal. 170 equals alkaline earth metal. Dirac-Fock calculations predict that it will most likely go 121 to 140 form the G-block superactinoids, 141 to 154 form the F-block superactinoids, 155 to 164 form the transition metals, 165 equals alkali metal, 166 equals alkaline earth metal, 167 to 170 p-block metals, 171 equals halogen, 172 equals noble gas. Not all models show the higher elements following the pattern established by lighter elements. Pekka Pyukko, for example, used computer modeling to calculate the positions of elements up to Z equals 172, and found that several were displaced from the Madelung energy ordering rule. He predicts that the orbital shells will fill up in this order: 8s, 5 grams. The first two spaces of 8p, 6f, 7d, 9s. The first two spaces of 9p, the rest of 8p. He also suggests that period 8 be split into three parts: 8a, containing 8s, 8b, containing the first two elements of 8p, 8c, containing 7d and the rest of 8p. Fricker et al. Also predicted the extended periodic table up to 184. This model has been more widely used among scientists and is shown above as the main form of the extended periodic table.